Welcome back, grade 11s from the break. Right, let's look at these intermolecular forces. So now we're talking about the forces between the molecules and how the substance is kept together. There are 6 different intermolecular forces. They range from really weak to really strong. So the first 3 are, another name for them are the van der Waals forces. But more specifically, we have got induced dipole, which is known as a London force, the dipole-induced dipole, and then dipole-dipole. I'm going to show you pictures of how these are formed so that you get an idea. These are really weak. Now, the in-between ones, the middle strength ones, they're all involved in iron. So have a look here, an iron. So we've spoken about ions. So we've had a look at sodium plus, chloride minus. Okay, these are ions. Now the reason why the iron-induced dipole and the iron dipole are stronger intermolecular forces than the van der Waals is because of the iron involved. It has a stronger force, and so that's why the intermolecular forces will be stronger. However, the strongest intermolecular force is what is called hydrogen bonding, not to be confused with intramolecular bonding. Okay, so this is very confusing. You just have to get it right in your mind. Hydrogen bonding is an intermolecular force. It is the strongest. Let's have a look now at these different types. So we're going to go from the weakest through to the strongest. So now when we have a diatomic molecule, the same atom bonded covalently to the same atom, it is a neutral atom because the electronegativity is going to be the same in terms of pulling the electrons. So here I have a picture of fluorine. So fluorine is bonded to itself. You can see the Lewis diagram here. You can see the overlap of electrons from the outer shell, and they share those bonded electron pair. Now, because fluorine and fluorine are the same, the electronegativity is the same, they're going to pull those electrons the same, and so they really do not have a resultant electronegativity. You can see there, if we calculate it, it ends up being 0. So what happens in these is, in a moment, as the electrons are moving through and being shared, there might be a moment in time where there are some electrons that are clustered in one place more than the other. And it is an instantaneous dipole, and there's then a ripple effect on all the other molecules that are next to it, because if there's an instantaneous pole being formed, a more negative side, then all the other molecules next to it, their electrons are going to be repelled or attracted if it's the positive side. Okay, so that's the induced dipole. It is very weak. It is called a London force, intermolecular force. Right, now what about a dipole-induced dipole? So these are polar molecules. So here's the polar molecule I've shown you here, and we indicate its side by a delta positive over there and a delta negative. So the delta is the little Greek letter, the triangle is the capital Greek letter. This is the little Greek letter, delta. You can see that this is a polar molecule. It has got sides poles that are one that's positive, one that's negative. If it comes across something which is neutral, guess what? It is going to draw those electrons towards it. So all the electrons are going to scoot to that side because that is the positive pole, and it's going to leave a resulting positive side on the other side. So this is a polar molecule that affects a neutral molecule. It is temporary, and it is also a weak force of attraction. Next one that we have is dipole-dipole. Now, this molecule that I have here is hydrogen chloride. If we look at the periodic table, we'll see that the chlorine has got a higher electronegativity than the hydrogen. So this is quite a high electronegativity. Electronegativity, there we go. And so it is going to pull the bonded electron pair over itself. It's going to pull it. And so this hydrogen gets left with very little electron cloud. And so we have a delta positive side to this molecule and a delta negative side because the chlorine is more electronegative than the hydrogen. When these particles, these molecules come into contact with one another, they are going to attract the opposite side. So if I draw this molecule on this side here, a bit weirdly, okay, so that's the hydrogen, this is the chlorine, this is the electron cloud, so this is going to be delta negative, this is going to be delta positive. What happens? There is a force of attraction between the poles. Okay, so that is the dipole-dipole attraction. It is also a relatively weak intermolecular force, but it is dipole-dipole. It's a bit stronger than the London. Now, iron dipole, I said to you that when ions are involved, that these forces, intermolecular forces, are stronger. Because of the size of the ion, it has a strong force. So we talk about dissociation. So when we've got an ionically bonded substance and we dissociate it in water, it will form its component ions, so Na plus here and Cl minus, and you can see it in the picture. Now when we have water that is with these dissociated ions, we know that water looks like this. Here it is here. It is oxygen and hydrogen. Oxygen is more electronegative than the hydrogen by quite a far bit. They are oxygen and nitrogen and fluorine are the most electronegative substances, and so the oxygen is going to pull the electron cloud over itself, exposing the hydrogen. We call it as an exposed proton, a naked proton, exposing it, and that electron cloud is really sitting heavily over the oxygen because it's really greedy for those electrons. And so this polar molecule, it's very polar, will then surround the ions. And you can see there what's happening, that there is going to be a connection between the positive, delta positive hydrogen and the negative chlorine. You can see there that these are going to be quite strong forces, and the same with the oxygen. The oxygen is delta negative, remember. It is going to form a force. There's going to be a force of attraction between the sodium plus and the delta negative of the water. So that is the interaction there, the friendship there is iron dipole, because water is the dipole. Okay, there, water is the dipole. It has got poles, and the sodium chloride forms the ions, and that force of attraction is called the iron dipole intermolecular force. Right, now an ion-induced dipole. Now I've got this really interesting molecule here. It's an organic molecule. It is hexane because there are 6 carbons involved, but this molecule is really non-polar. It doesn't have any side that's sticking out that is saying it's going to be polar. It is quite an evenly bonded molecule, and so it's non-polar. Now what about the ion? So if we put the ion into the ionic substance into water again, we get the sodium plus ion and the chloride minus ion. And if these ions come into contact with this non-polar substance, let's say it's sitting over there, what's going to happen? Well, the electrons that are involved in this molecule, they are going to be attracted towards that side. Okay, so the electrons are going to be attracted towards that side. So what's happening? An induced dipole is happening here. It's not a polar molecule, it's non-polar, there's no pole involved, but because the ion moves past it, it is going to cause those electrons to be attracted towards it, and there's going to be a positive and a negative side to this non-polar molecule, so it's an induced dipole. Okay, the same would apply if it was the chloride ion. The chloride ion would repel the electrons, and so there would be a side which is positive and a side which is negative. So that would then be the induced dipole. Now, hydrogen bonding is unique. It is the strongest intermolecular force, and there are very particular behaviors that go along with the molecules that are that have this setup, and the hydrogen bonding in between them is so strong that you can see their behavior is very different. So I've given you a picture of the water molecules and their interaction. Here's their friendship over here, okay, their interaction. Now, the thing about this hydrogen bonding, it happens with three atoms. And the three atoms that it happens with are the three most electronegative elements, and those are nitrogen, they are oxygen, and fluorine. So those are the three most electronegative elements around. I thought I had a table, periodic table here, but you'll see on the periodic table, the electronegativity, you'll see that they are the highest. The other condition for hydrogen bonding to take place is that these three elements have to be bonded to hydrogen. And the reason why is hydrogen has got one proton and one electron. And so it is very, very small. So when the highly electronegative atoms, the elements, when they draw the bonded electron pair, they actually leave that hydrogen naked. It is a single proton. That's all it is. This poor thing is a single proton. The other condition is that these are pretty small, because if we look at the group, if we look below nitrogen in its group and below oxygen and below fluorine, we see that those elements, the atoms of those elements get bigger and bigger and bigger, and they don't display the same behavior. They don't have hydrogen bonding between their molecules. So these are really small, and it means that their interaction is very close. We've got the single proton on the outside. Here's the single proton on my diagram. We have a relatively small oxygen. It means that this interaction here, I'm just going to color it in, this relationship is very close. So that hydrogen, that proton gets really close into the oxygen atom, and that the interaction, that friendship is strong, very strong. That means that these three molecules that result, let's write them down. It would be nitrogen bonding to hydrogen, and that is ammonia. It is oxygen bonding to hydrogen, which is water. And then the last one is going to be hydrogen fluoride. I'm just going to write it here, hydrogen fluoride. Hydrogen fluoride, those three means that they can get really close together, and the intermolecular force is very strong. That is hydrogen bonding. Right, grade 11s. In our next lesson, we are going to tackle some problems. Hope to see you then.